already mentioned, today we're going to talk about how to estimate the performance of ML models that are deployed to production. And this is kind of a deeper dive on what you saw in previous webinars. So it's both a theoretical and practical deep dive into how this thing actually works. And we're going to be using NannyML as a way to do it. So before we delve into the agenda, let me just kind of answer the implicit question of why you should care and why you should try to estimate performance of your models, and why just typical drift detection or monitoring of realized performance is not enough. So imagine that you work at a bank and you own a use case for predicting mortgage loan defaults. So what you take is you take credit scores, customer information as your model inputs, and then you try to predict loan defaults. But you work with long-term loans. So let's say that you work with mortgages that are 20, 25 years in the future. Then typically in such financial institutions for these targets, you actually don't want to predict something 25 years ahead, but just people who are already delayed in repayment, let's say after 2 years. But nevertheless, you still need to wait 2 years before you know the quality of your predictions. And that means that simply calculating performance is not enough, because it might be way too late when you realize something goes wrong. Imagine something goes wrong 3 months after deployment, and then it keeps on being wrong, and instead of making money, losing money for 2 years. That means that you might lose multiple millions before you realize it, and when you realize it 2 years later, it's already going to be too late. So what we need to do is we need to try to estimate somehow the performance, the quality of our predictions before we get the ground truth. And this is what we're going to be focusing on today. So, quick agenda. First, I'll go over the general question of why ML monitoring is vital. Then we're going to quickly examine, kind of mostly glance over, two main causes of silent model failure. So why model degradation and model failure are a thing, what actually causes it. And then we're going to try to actually go into estimating performance of models without ground truth. And we're going to split that into two parts. First part is going to be about regression models, and we have an algorithm that we developed for these regression models called DLE. We're going to go over the theoretical basis for the algorithm, how it's actually implemented, what are in the inputs, outputs, and then we're going to have a quick tutorial of how to use it in practice. And then we're going to do the exact same thing for classification with kind of a sister algorithm called CBPE. And then we're going to have, again, a quick tutorial, and then we're going to have 5 to 15 minutes for questions. So let's get started. Why machine learning monitoring is vital, part 1. So let's start with the goals. Why do you actually need to monitor machine learning models? So the first and most important goal is to maintain the business impact of the model. If you deploy your models to production, you want them to actually have some kind of impact on reality, on the business, on the organization you work with. And what you want to do as a data scientist is you want to your either automation or prediction use cases to continue to have this business impact. And to do that, you need to know what's going on. So ML monitoring. Another thing is that you want to reduce the risk of the model. So every model, because it works with either stochastic algorithms or it makes decisions based on data with a lot of noise, has certain inherent level of risk. Maybe it's the risk due to the fact that the predictions are unstable. Maybe there is just by random chance, there might be more people who are harder to predict on, and that will influence the outcome. There's always a risk of the model, and we want to reduce or eliminate this risk by really knowing on what's going on and being able to quantify this risk. And the last thing, kind of from your perspective as either data scientist or head of data science, you want to also increase the visibility of the model, just to be able to prove the impact of you as an individual contributor or as a manager on the organization. So the more visible the model is, the more likely it's going to be to get you a raise, promotion, increase the budget of your team, and things like that. So you want to basically make sure that your work is appreciated. And for that, ML monitoring is also important. Now, how do we do this? So we at NannyML have quite opinionated stance on that, and we believe that you should always start with performance. Performance is the best proxy. We're talking here about technical performance, so metrics like F1, accuracy, mean squared error. These metrics are there to approximate business impact. So focusing on monitoring those allows you to monitor the most important thing, which is the business impact, and protect the business value. Then only if something goes wrong, then we should go into root cause analysis. So if we know that there is some important change in performance, whether realized or estimated, then we need to figure out what has gone wrong. And for that, we use data detection algorithms, methods, and techniques. And then once we figure out what actually went wrong, we'll go to issue resolution. While, of course, at the same time, continue to monitor the performance. So the workflow is quite simple, actually. And that was the first part. Now, let's go to the second part, which is what actually can cause silent model failure or model degradation. And to do that, I'm going to quickly go over basics of machine learning, which is what we're actually trying to do when we build a model. So there exists a true pattern in reality. Let's say that this pattern is that we have one feature, feature X, and this feature X, as it increases, it's somehow related to our binary outcome, whether something belongs to a positive or a negative class. And there is certain underlying relationship between these two variables. As X increases, it is more and more likely that our data point is going to belong to a negative class. And the relationship, as we see here on the top plot, is kind of sigmoidal. Then what we do when we gather our data, we sample from this population, from this distribution. Maybe these are all of our existing customers. Maybe these are all the, let's say, wind turbines that we have access to. Maybe it's 1 year of historical data because we don't store more data. We always sample from the population in some way. And what we end up with is actual data, where we have this pattern captured in the data, but it's not the entire pattern, it's not the entire population. And the reason why I split it this way is that the two causes for changes for machine learning failure is actually either the change in the true pattern or change in sampling. Let's start with the change in sampling. If our sampling mechanism changes in some way, we call that covariance shift. That just means that the way our joint features look like, so our joint model input distribution looks like, is different. If we have one feature, as in our example here, that just means that the distribution of that feature is going to be different. And that means that even if the true pattern that our algorithm was trying to learn remains unchanged, we will still see different data, potentially different class balance in binary classification model, potentially different mean of the target in regression models. And that can also already influence the quality of our predictions. I'll go into why that happens later on. So again, just to formally define what covariance shift is, it is a joint model change in the joint model input distribution. So the probability of capital X using typical notation. And we see here that after the covariance shift, our distribution is going to look different. And you can already kind of qualitatively assess that before covariance shift, there was more positive class than after covariance shift. And that means that business might be impacted. Now, the second reason why machine learning models can fail is the change in the true pattern that we're trying to capture. And this is what we call concept drift. Here, if we have pure concept drift, there's no covariance shift and there's just concept drift, our sampling will remain unchanged and our data from the features perspective, so model inputs perspective, is going to look the same, but the class distribution and target distribution is going to change. And that, of course, means that, again, our models are very likely to have deteriorated because the patterns that they're captured is no longer relevant or is no longer very accurate. And again, here, just to define it, it is the change between in the relationship between the target and the model inputs. So I mentioned here specifically relationship. It's not necessarily a correlation. It's not necessarily even a function, because not all relationships are functions. It's just any relationship they have. If it changes, we have change. We have concept. So using typical notation is the probability of Y of the target given X given joint model input distribution. So now we covered the two main reasons why models can fail. Now let's go into the main part of the presentation, which is how we can actually detect changes in performance due to these reasons. And we're going to start with regression using our algorithm called direct loss estimation. So first, what can we actually estimate? We can estimate any technical performance metric that we use to evaluate regression models, with exception of R-squared. Likely R-squared is not widely used to evaluate models that actually go to production. So we can use root mean squared error, we can use mean absolute error, we can use logarithmic errors, basically any kind of error metric that you have, as long as you can define it on point value, we can estimate it. And what you see here, just an example, we're going to have these estimations, we're going to have confidence bands around our value, and hopefully it works quite well. So what does it actually do? So this algorithm strives to capture, and generally does capture, the full impact of covariance shift on performance. So as you already know, there's two reasons: covariance shift, two reasons why machine learning models can fail or deteriorate: covariance shift and concept drift. This algorithm focuses only on capturing the impact of covariance shift on performance, and also implicitly assumes there is no concept drift. So if your data has very strong concept drift, this algorithm will not work very well, unfortunately. But it still does something, and it is significantly better than doing, for example, data drift, which also can never actually account for concept drift. And also it assumes that there is no covariance shift to previously unseen regions. So imagine that you have a region in space that there was absolutely no data for, or very few data points for. In these regions, the model probably did not learn the pattern correctly. So if there is a strong shift there, the algorithm will not be able to fully take into account the deterioration of performance, fully take into account the impact of covariance shift. But as long as covariance shift is strong, but it's covariance shift to regions we've already seen in the past, this algorithm will do quite fine. So now we know what it does on very high level. Let's talk about what we need to make it work. Basically, we need to provide it with three things. We need to provide it with model predictions, so our actual target predictions. We need to provide it with the feature column that we use to develop our models. The same features that you use to develop our model, just pass it here. Very simple. And then it's an algorithm that also learns. It's also a machine learning algorithm. So there is a fitting stage. And for this fitting stage, we need to provide the ground truth or the target. It's the same thing. Depends how you call it. For fitting, and then it's going to learn a specific pattern, and then you'll be able to use it with just model predictions and feature columns. And now, what does it actually output? So familiar visualization, but now let's go slightly more in depth here. So first thing it outputs is actual estimate metric for each kind of a chunk of data or period of data. Let's say it's a week, for which you want to know what is the performance. Of course, performance is something that's potentially very noisy. So we need to aggregate our data to have a reasonable estimate of what is the average performance of the model in a given week, given hour, given 10,000 data points, however you pick that. It also provides automatically determined threshold of acceptable performance based on basically the variability of performance in our test data set or our reference data set, for which we know the performance was acceptable because we verified that. And typically for that data set, for this so-called reference data set, you want to use your test set, because then you know obviously that the performance was satisfactory. And now let's kind of start to establish the intuition behind the algorithm. So what you see here is a very simple model that just takes one feature and tries to predict a continuous target. So we're dealing here with a very simple regression problem. Let's say that we train our linear model. Our linear model is going to learn quite correctly, and it's going to output this pink line over here in the middle. But one interesting thing about this data set is that not only the target is a function of the feature, but also the noise in the prediction or uncertainty of the prediction also changes as our feature one changes. So the higher value of the feature one is, the more spread out the predictions are. There is a word for that that starts with heteroscedasticity that I can never pronounce. That means exactly that, that the noise in the function is dependent on features themselves. And this is actually true for almost all real-life use cases. And this is the fact that we leverage in our algorithm. And what we do is we basically train another model that takes the error in our prediction for every single data point, and we tries to estimate this error based on inputs, based on our features. So then what we can do is we can estimate the loss based on our features, and that's how we can estimate performance, because if there's regions in our space when the loss is higher, or the expected loss is higher, the uncertainty is higher, we're going to see lower performance. And just to give you a visualization of how we can actually compute a metric, imagine that your test data or your reference data on the left here are the violet dots. And we also see the expected error or model confidence here in these line plots or contour plots, I think they're called. And we see that most of the data points are in the green region when there's low inherent noise in the data. The model can very easily learn what is the correct pattern and can give our very consistent predictions. And then we see here this kind of mountains on the left and right. And here we see that we don't have a lot of data, but we know that these regions are very hard to predict on. And as we deploy our model, it starts making prediction. There is some kind of covariate shift, so change in our feature distribution. And we see that there is more and more data points in the left and right sides of the feature space. And that means also that the inherent noise in the data is higher there. So our models will make more mistakes, and our average error is going to increase in case of regression data. And we can quantify that. And now I'm going to explain exactly how we go about quantifying that. But I hope that the intuition is clear by now. So the algorithm, it basically just takes 3 steps. First is we're going to take our test data, our reference data, and we're going to calculate our loss metric on this reference data. Let's say it's mean squared error. And we're going to calculate this squared error without taking the mean for every single data point separately. Then we're going to simply train a model to estimate this squared error, so this loss metric, using the features of the model and the actual monitored model predictions, because the model, you could treat it in a way as very powerful use case specific way to reduce the feature dimensionality reduction method, basically. So we also take the model predictions because maybe there is some information there that our model would struggle to extract with just the features. We take those two and we actually try to predict the squared error or whatever metric we choose on our reference data and our test data. And then we take this fitted model and we just directly estimate error for every single data point on the analysis data. Then we take the average of that in a chunk in some kind of period, as I already mentioned. And this is something that we can output with reasonable certainty. So that's basically how the regression works. And now I'm going to go into the tutorial. First, where is that if you want to take a look? We go to our NannyML examples repository, we click on webinars, and here you will see how to estimate the ML performance of deployed models folder. Click on that, and you will see performance estimation regression notebook. You click on it, and that is the notebook that I already show. I have it running locally. So let's just get it started. I run it just to make sure that it actually doesn't break, because when you show stuff in live presentations, code always breaks. So let's hope it doesn't happen now. So quick walkthrough. What we're going to do. We're going to just to show you kind of the end-to-end process. I'm also going to train the model first. I'm going to prepare the model for training. I'm going to train it. I'm going to make predictions. And then I'm going to simulate kind of a production environment for which we don't have ground truth. We're going to estimate performance, and at the end, we're going to compare this estimated performance with realized performance to see whether the estimation was reasonably correct and whether we could have used it to really figure out what's going on with our model. So now let's go through step by step. First, we import the data. We just import some libraries to read the model. We import pandas. We import something to train our model. And this the case is going to be like gradient boosting. We're going to actually load the data, not import the data. And we just load it with whatever loading library we have. And we see the data here. What we're trying to predict is number of bikes shared in some kind of bike sharing application. Before we go into the model building, we'll have to drop some things for ease of modeling and just for presentation purposes. I'm dropping everything that's not a number because I don't want to deal with encoding and stuff like that. I will also drop features casual and registered just because you can just add them up to get the target. So we'll be cheating a bit if we included them. So let's drop them. And I'm just going to actually run this. Hopefully it still works. And now let's split the data. So we're going to split our data set in our train subset, our testing data set, and our production data set. Again, I don't have validation. I'm not optimizing hyperparameters. I'm just doing the minimum thing possible. And then we just train our models with default parameters, some random state, and voila, it's trained. It's not a big data set. Then we're going to make predictions for our training data set, for our testing data set, and for our production data set. Now, what we need, as I already mentioned, we need our reference data set. And as I, again, already mentioned, we can use our testing data set as our reference for which we want to say that performance there is for sure satisfactory. So we are preparing our data by defining what is the reference data set. Just literally call it reference. We'll copy our test data set. And there's two things that we need to add to it, which is our predictions and our actual target. So here we take the features, we add our predictions, and we add the target. And that's it. And we're going to do very similar things for our analysis data set, so the data set for which we want to know what's going on, what's the performance. And again, we just take the features and we add our predictions. An important thing here, of course, we don't add the ground truth because the ground truth is not there yet. It has not arrived. It is delayed. Then we have our data preparation ready. It was really that simple. Then the next step is we're going to initialize and fit our algorithm, our direct loss estimation algorithm. And what do we have here? So inputs, again, as in the slide, we just need to provide what is the column with the predictions. We call it ypred in a very creative way. What is the actual true column? What's the target? We call it the target. So we just provide the name. And what are the metrics that we want to estimate? In this presentation, we have MSE, MAE. We could add some others, but let's stick with those two. And we need to provide all the columns that were used as features in our models. So we're going to do exactly that. We take our trained data set, find the columns, and cast it to list because this argument accepts a list. We initialize it, and then we fit it. It's fitted. That's it. It's done. Then we're just going to estimate. So this is kind of like a dot predict in scikit-learn. Here we're actually estimating. So we're using dot estimate method on our analysis data set. And let's run it. And it's already estimated. And NannyML provides a very cool way of visualizing the data. So we can, again, run this. And we will see that for both metrics that we have here, MSE and MAE, we see a plot of how the estimated data looks like for our reference or test data set and our analysis data set. We can control the size of these chunks here, but we don't have to do it. And it seems I'm very lazy, even for a data scientist. I don't control it. I just go with default value. And we see that we have around 700 data points in every single chunk. And we see that our MSE, after the model has been deployed, even right before deployment, has gone up significantly. And that means that there is potentially a problem. And the same goes with MAE. So we see there is issues. Now, question is, should we trust it? Of course, even if we don't know, we have no way of verifying that, so we should go and investigate. And this is something that I'm going to talk in our next webinar. But for the time being, let's see if we should have trusted and if going with the kind of recommendation of what is the expected performance is a good idea. So now I'm going to just calculate the performance. Again, using NannyML, I could do it using scikit-learn, but this one gives us very nice visualization, so I'm going to go with that. And again, we need to initialize it. What is the prediction column? What is the actual target column? What are the metrics that we want to calculate? And what is the problem type? We're going through a regression tutorial now, so this is a regression problem. And we're going to fit it. Why do we need to fit it, you might ask? Because we want to establish what are reasonable thresholds for performance. This is the only reason for fitting. And then we're going to actually calculate the performance. This time we actually need targets because we're not estimating anything, we are calculating stuff. So I'm going to add or assign additional column here, which is the target. And now you see realized performance, and we can do a quick comparison. MSE looks kind of like that, that there's two spikes here and there, and so does MAE, so they're very similar in our behavior. And we see just from these two plots that MSE was a bit pessimistic, especially here, but it managed to catch the first strong deterioration of the model and also the second one, and then it managed to kind of find out that the model is predicting slightly better than before. So this is something I would definitely be happy with, to have access to something like that 2 years ahead. Even if the prediction is not perfect, it definitely tells us that something has gone wrong, and we need to be able to figure out what's there and that there is an issue. And the same, of course, goes for MAE. Again, the same pattern, that it finds the first peak, then it kind of recovers and finds the second peak. That's really it. That's how you estimate performance using NannyML for models without ground truth. So now we only have one more part to go, which is classification. Performance estimation with an algorithm called confidence-based performance estimation. We are very creative at naming our algorithms, as you probably already noticed. So let's figure out how this actually works. So first, I'm just going to go using the exact same structure as before, which is what can we calculate? What are the metrics that we can actually estimate? So first and foremost, we can estimate confusion matrix and a kind of actual confusion matrix for binary classification only. And for multi-class, we can get any of the matrix that are used, and for binary as well, that are used based on confusion matrix. So precision, recall, accuracy, no, I can't pronounce it. That one, F1, and NAF measure. And we can also calculate and estimate ROC AUC, which is also widely used way to evaluate the quality of our models. And we have familiar visualization here. What does it do? Exact same thing, so I won't go in depth here. Captures full impact of coverage shift of performance, assumes there's no concept drift, and assumes there's no coverage shift to previously unseen regions. We operate with the exact same set of assumptions, and we're going to actually leverage similar kind of ideas, but in slightly different manner. So here you see the first difference when it comes to inputs. We actually not only need our predictions, but we also need the model scores. So quick recap, model scores are the numbers between, for just to use binary classification as an example, they are the numbers between 0 and 1 that are supposed to represent the probability that a given data point belongs to a certain class. So let's say if you have 0, you have binary classification and you have output 0.3, it means that there's 30% that a given data point belongs to a positive class. So we also need those, and likely most of the classification algorithms that we use nowadays, especially on any kind of data, provide those scores. We also need model predictions, and we again need ground truth / target, and again, it's only for fitting. And interestingly, we don't actually need our model columns here, so our features. because we implicitly get them via model scores. And again, it outputs the exact same thing: thresholds, confidence bands, and the point prediction, the estimated metric. Now, let's build up the intuition, and the intuition is very similar, but slightly different. So we see familiar visualization here. When we see on the left test data, on the right production data, we see region that is where the model is very confident, and the region where the model is not so confident. And we're going to see covariate shift towards regions that are not confident. And let's say that the region that's not confident is just a region between two classes. It's close to the class boundary. So of course, the model struggles to correctly predict to which class a given data point belongs, just because of inherent noise in the data. But the difference here is that instead of estimating this contour plot using by training another model using the input features and the model predictions, we're going to directly leverage the model scores, because the model scores already give you this contour plot of model confidence. So that's what we're going to do. That's our intuition. So we're going to, again, leverage that directly. And let me explain how we do it, because there is quite significant difference here. So first of all, as I mentioned, these model scores are supposed to represent probabilities, but unfortunately for most of the algorithms, they actually don't. So what we need to do is we need to calibrate those probabilities. So if you get, let's say, value 0.4, it actually does mean that on average, 40% of data points with value 0.4 will end up being positive. That's just literally the definition of frequentist probability. And we need to make sure that these model scores abide by the definition. Then we're going to choose our threshold, because to make predictions, you need to threshold your scores. So we're going to choose a threshold. Then we're going to do a kind of weird thing, because for most of the metrics for classification, it doesn't really make sense to define them on point-to-point basis, because it's just going to be either 0 or 1, 0 or 1. Let's say you want to have per point accuracy or per point precision. Either the prediction is either right or wrong, and it doesn't really make sense to look at it from per point level. So instead of finding the confusion matrix for every point, we're going to find the expected confusion matrix, where the value doesn't need to be 1 or 0, but can be a floating point value. And then we're going to aggregate to find the actual full confusion matrix for our chunk of data. And then from this confusion matrix, we can compute any metric we want, including ROC AUC if we add some stuff here and there. So I'm going to now walk you through every step, starting with probability calibration. So here what you see is so-called calibration plot. I took it directly from scikit-learn. There is no new science here. This is all rather simple. So what you see is we bucketed, or we binned our predictions in certain buckets, or let's say every 10% or every 20% in our predicted probability. So let's say we have a bucket here between 0.2 and 0.3. And in this bucket, the average value of the predicted probability is 0.3. And what we want to achieve and what we expect from actual probability is that if we look at ground truth at realized classification results, or at targets, we would expect to see, let's say, the 0.2 positives, but we don't. We would expect to see a very straight line here. But we see kind of the sigmoid shape for support vector classifier. And that just means that this algorithm is not properly calibrated. So what we need to do is we need to use very simple regression using this exact plot and these exact bins, and we'll try to straighten that plot to make sure that it forms straight line from 0 to 1. And if we see that the mean predicted probability for a bucket is 0.2, we actually do observe 20% positives predicted on our test set. So that's what calibration is about. So that's the first step. We do that. NannyML handles that internally, so no need to worry about it beforehand. Then we pick a threshold. based on our business, based on our metrics, which is we pick a threshold that maximizes the metric. Let's say the metric is F1. You're going to pick such a threshold that maximizes your F1 by just iterating, or you just pick 0.5 because why not? Then we already know that our predicted probability corresponds in long term over a large number of samples to realized fraction of positives. So we know that if it says it's 0.9, there's actually 90% chance that a given data point is going to end up being belong to positive class. Then we're going to threshold it, and we will know for a fact that a given data point belongs to positive class. So from that, we can actually say that, again, we know that for a fact, there is 90% chance that this is a true positive and 10% chance it's a false positive. And based on that, we can find the expected confusion matrix for every point. And again, we know that we can assign the expectation of 0.9 to true positive and the expectation of 0.1 to false positive, because on average, in long term, that is exactly what's going to happen as long as our predictions are well calibrated. And we also know for a fact that it cannot be a true negative or a false negative because it's above our threshold. So the algorithm itself will always make a positive class prediction. Then we do it for all of our data points in a given chunk. Again, we want something like 700 or more data points. And we just sum it. And what we get here are these, this is kind of this weird confusion matrix with floating point numbers. But again, working with expectations. So we can directly take that expectation and convert it to a metric, such as precision, recall, F1, etc. And again, let's take a look how it looks. I'm going to go slightly faster here because it's going to be, again, the same flow. We are still in NannyML examples, webinars, how to estimate ML performance of deployed models. And now we're going to click on classification. And going to classification, again, let's hope it doesn't all fail. First, we're going to import our data. We're going to do the same thing. The only difference is now we're trying to classify our model. So I'm going to use light gradient boosting machine with classification. I'm going to load data. This time we're trying to predict whether electricity in Wales, these are, by the way, all real life data sets that you can find on openml.org, which is very nice repository of open data sets, in my opinion, much nicer than Kaggle. So check it out at some point. We're going to load the data and we're trying to see what's the prediction. It's either up or down. We get some numerical columns because it's already has been pre-processed. So the data set already is this kind of pre-processed form. We're going to process our data. So just we want to get 0 ones in our class. So if it's B up, it's 1. That's it. And we're going to drop our day because we're lazy and we don't want to deal with features that are not numerical. And we obviously need to drop our class to not cheat. Then we're going to split the data, same story as before. We're going to train the model, again, same story as before. We're going to score and predict. So we need to make separately the scores. So we use the predict probabilities. It features heavily in the algorithm, so we definitely need to have them. And we're going to just make the actual predictions using implicit threshold of 0.5, as you normally have in most of the algorithms. Then we'll prepare the data for NannyML, exactly the same thing as before. We take our features from the test set, we add the predictions, we add the ground truth, and we also add our model scores. So again, just to mention here, these probabilities don't need to be calibrated. The algorithm itself calibrates the probabilities. And again, these are model scores over here. I need to push it afterwards. So we have this data and we're gonna initialize and feed CVP. And like I mentioned, we need our model score name, so ypred proba column, which is just called ypred proba. We need our predictions, which is just ypred. We need to know what's our target, and we need to know the metrics that we're trying to estimate here. And just choose something that's like not all based on confusion matrix directly. I'm going to use ROC AUC and I'm going to use F1. And imagine this time that the story is slightly different. It's not that you're trying to predict something far in the future, but you deploy the model, you kind of forgot about it, and it just keeps on running. Nobody's really looking at it. So we're gonna estimate the performance. By the way, that's another thing I wanted to show you here. You can also just do 2 data frame at the end of your results. Let's say that you only want to look at our analysis. So you can filter the results for analysis, turn it into data frame, and then display it. And you get very nice data frame that you can play around with manually if you want. And for every chunk of data, you will get the index keys. Let's say we don't have timestamps. If you have timestamps, you can also use timestamps here. And you will get all the information about the performance, the thresholds, the confidence band. So we'll use sampling error for that, and the actual value. Now let's see how this looks like. And imagine that this time you actually did not monitor the results, and we see that everything is going fine. For ROC AUC, there is maybe a slight dip at the end, but actually on our test data set, the model was not performing as well as we would like it, but we're still happy with it. And F1 actually increased very significantly after deployment. And that kind of tells a different story, in the sense that you still need to monitor the predictions, because you might be missing out on certain opportunity on upside. Imagine that you're very conservative with your credits because you knew that the model is not that correct, and there is significant risk in giving credit to somebody or buying electricity, as in that case, on trading all electricity. Your bet size was very small when you're trading electricity because you knew your model is not very good. And it has ROC AUC that's significantly above 0.5, but it's not that great. But maybe you evaluate it by F1. And we see here, most probably because of the change in class balance, F1 just shoots up extremely high. And that means you might actually want to change how you deal with that downstream. And if you were not estimating the performance, you wouldn't be able to find out. And again, just to validate that this thing actually makes sense, we're going to follow the same flow, and we see that ROC AUC slightly goes up, and so does F1. Here, ROC AUC, we didn't actually estimate it very well in the beginning, but then we find this peak and we find this drop. And with F1, we basically get it perfectly. There is peak, there is drop, there is peak, there is drop. It's almost perfect estimation when it comes to F1. When it comes to ROC AUC, made a mistake here, but it's still quite useful. And you've seen that the algorithm can be potentially useful not only when the model fails and not only when the model degrades, but if anything unusual happens, such as the performance improving. And that is really it. So now I'm going to be slowly wrapping up. Thanks for listening. I would really appreciate if you give NannyML a try at GitHub/NannyML. And if you also give us a star, would be great. There is a QR code here that you can just scan. I'm going to give you a second to scan it if you want to go directly to this GitHub. If not, I'm sure you can also find it via Google or any other search engine of choice. And there's one more thing that I'd like to share, which is I'll be hosting kind of a part 2 to this webinar. When here we're really focused on monitoring the performance, but we didn't really go into resolving the issues and root cause analysis. And in the next presentation or the next webinar, a week from now, next Thursday, I'll be talking about how to detect drift and resolve issues in your machine learning models. And for that, we assume that we already know what's going on with the performance, either by calculating it or estimating it. And we need to kind of figure out what exactly went wrong so we can resolve it. So again, you can already directly sign up to it. And I would love to, also talk to you there in a week. So yeah, I think that's it. And now it's time for me to give stage again to Mafalda and answer some of your questions.
Yes, thank you so much, Wojtek, for this awesome presentation. We do have a lot of questions here. I will start from the beginning, and we have a very cool one that is, what is silent model failure? So I like this
Yes.
one very much.
So that is something actually I probably should have explained earlier on. Sorry for that. The idea is that when performance changes, you will not see errors. Your model will still make predictions. And especially if it's some kind of degradation that doesn't completely destroy your business immediately, and hopefully it's not, you will not really notice that unless you look very, very closely. So it's not loud, it doesn't show itself, it fails silently. The model degrades silently if you're not looking at it with good tools like our performance estimation, you will not notice that it's failing.
Nice, very nice. The next question is from Laura. Thank you so much for the presentation. Quick concept clarification regarding the DLE slides. If I understood correctly, the DLE assumes you have fully representative data, as it assumes that there's no covariate shift on previously unseen regions. Is that true? Thanks.
So yes, that is an assumption, but in our experiment, it's a weak assumption, which means that even if it's violated, as long as it's not very strongly violated, DLE will work reasonably well. So the data might not be representative in a way that you have a few data points and the model can learn something about the expected error. It doesn't need to learn it perfectly. It doesn't need to have enough data points to capture the pattern perfectly. As long as it can capture it in some way, it will still work reasonably well. And if anything, it will overestimate the error. So with errors kind of on the safe side. But again, this just comes from our internal experimentation. When we validate the quality of our models, that's what we got. And we don't put it out there publicly because we don't have, peer-reviewed process for that yet. But generally, it is an assumption. It's not a strong assumption.
Nice. Thanks a lot. Then the next question from Sonia. Can we use custom metrics for the DLE, not only MAE or MSE?
Currently not. It's something that we definitely have on our roadmap. And if it's a strong need for you, please submit an issue on GitHub. And we'll definitely take a look at it. And for others, if you also feel strongly about having a need for that, do upvote the issue. This is literally how we decide on our product roadmap. And so if you find it important, do submit the issue and we'll work on it. And we also, of course, are welcome to contribute directly because we're an open source project.
Great. The next question is it possible or is there some way to apply NannyML to clustering algorithms?
That's a good question. You'll have to hack it a tiny bit because right now we don't support it explicitly. But what you could do is you could, as long as you have some kind of metric to evaluate your clustering when you develop a model, and you generally should have, you either have some supervised way of doing that because you know the ground truth for clusters. And if you don't, you can use something like, let's say, a silhouette score, where you can do estimate the metric in an unsupervised way. And then you can use that as a target, and then you'll be able to apply. I think DLE would be better there for unsupervised learning algorithms. And I think it should work. Do give it a try, let me know how it goes. And if you have any issues, we also have a community that Mafalda will share in chat in a second, the link for. And if you struggle, do leave us a note there and we'll do our best to help.
Great, thanks a lot. The next question is, maybe you will need to share the slides. Can you please show us how to read the MAE and or MSE plots that show drifts in some more detail?
Yeah, so the plots, to be kind of, technically correct, don't actually show drift, they just show change in performance. And then we need to figure out using our domain knowledge and using the drift plots and the actual drift metric that I'll go over in the next webinar to figure out what exactly went wrong. So If you want to know more about how drift relates to performance, definitely do attend the next webinar when we go much deeper into how drift works and how drift can potentially relate and explain drops in performance.
Nice, very nice. The next one from Sonia. Do you deal with multi-output regression problems, not only one target?
Yes, and this requires a tiny bit of hacking, but significantly less than normally, which is just assume that there are multiple problems with the same features, same inputs, and different targets, and just do it one by one separately. Of course, it won't be as good as if we treated it as multi-output regression at the same time, because we miss all the interactions between the outputs. But you can do it if you just take model inputs and do it one by one for every target, and that way you can monitor those.
Nice. Okay, we're almost there. These are awesome questions. Thanks a lot, everyone, and keep sending them if you have anything that wasn't answered. The next question, Wojtek. How did NannyML improve the performance as we checked through MSC, but how was it achieved internally? Also, there was MSLE method shown. If you could make us understand when that comes in picture in NannyML.
Yeah, I'm not sure if I follow that question fully. I'm going to start by answering the second part, which is, but there was an MSLE method shown. Yes, so basically you can use multiple different metrics for to monitor. You can use NannyML and you can use DLE to monitor multiple different metrics such as MSE or MSLE, so the logarithmic error. And it just depends on your business use case and the metric you care about. You just put it there as a string and it's gonna output a specific metric. So that's second part. The first part, maybe there's a slight misunderstanding. So NannyML focuses on monitoring performance, not necessarily improving it. So if something goes wrong, we'll be able to tell you what went wrong, but the improvement part will cover partially in the next webinar when we delve deeper again into what exactly went wrong. But then when it comes to resolving the issues, that is something that, at least for the time being, you still have to do as a data scientist.
Yes, exactly. Nice. I think that was it, but do let us know if it wasn't answered. Another question. Out of curiosity. Yes.
No, go ahead. There was another question. That's all I want to say.
Yeah, there are like still a bunch of questions, so we can still be here for a while. Out of curiosity, the next question, how do you obtain the nice visualizations such as slide 29? So I think they're mentioning the nice plot you had, green and orange.
Yes, this one, I think.
Exactly. Yes,
yeah.
slide 29.
So basically what I did is this: I used scikit-learn and make classification to create binary classification with like kind of overlaying plots. You create predictions for it with properly calibrated model scores. And then you do, I think there is a method in matplotlib called contour plot. And then basically that's what you're gonna get, except the colors will be slightly ugly. And then we leverage our wonderful product designer who made this slightly more beautiful. But the idea is actually create classification problem, make predictions, make sure that the predictions are actually properly calibrated. Sorry, the scores are calibrated, and then make contour plots around them. And that's how you get it.
Nice. Everyone is very jealous about your nice craft. Okay, next question. Does NannyML use MLE for regression problems and CBPE for classification problems? And is there specifics for the same?
Okay, that's another question that I struggle with a bit. So we use DLE, direct loss estimation for regression problems, and CBP for classification problems. So it's basically, I'm not sure if I understand the question here.
Yes, I think it's mainly like, Are there any more specifics in between the two differences?
Okay, so
algorithms?
if there are, what are the main differences? So the main difference
Mhm.
really is CDP kind of leverages the model scores directly and assumes that you have these model scores because most classification models already output model scores. So instead of retraining another model, we just calibrate the probabilities of your model. Then we don't need the features, and we can basically leverage all the hard work we put in building your model to capture things very well and take that directly to estimate performance. Whereas with DLE, we need to automatically, kind of in AutoML fashion, create a model that directly captures the loss of any data point. So there's more work there on actual automated model building and a bit less work in taking your outputs and transforming them into something that we can use to quantify performance.
Awesome. Thanks a lot. Okay, the next question. Is there any way to check the performance metrics for recommendation engine?
Not directly, no. We don't support metrics like, I don't know, precision at 5, precision at n. It's something, again, I would like to ask you to create an issue on GitHub, and we'll prioritize it and get to it because we're getting questions for multi-output things, as you already noticed, recommender engines, unsupervised learning, NLP problems, computer vision problems, and we need to juggle those. So if you put it as an issue and are voted or active there, we'll definitely prioritize it over other potential things that are requested by our users.
Nice. Thanks a lot. Another question. Can you please explain one of the estimated performance plots in details, please, step by step, if possible?
Here we go. Okay, so we have, let's go with regression. Here we have the estimated performance plot. So we can just plot it, and here's what we see. On the left side, we see the metric of choice. Here we see the name that is actually estimated and our metric of choice. So MSE, mean squared error. Now we have two parts of the plot. You can plot only one if you want, but you can, by default, we'll plot everything. So you have our reference data set on the left here, which is, for example, our tests in our example. So this is something that you always know about. This is what you tested before the model went to production. And this is our analysis data set. So the part of the data for which, let's say, you don't have ground truth for, so we need to do actual estimation. So this is kind of these two parts of the plot. Now what you see is this red line here that splits it in half here, a bit more than half here. This is the threshold. This is something that NannyML automatically determines what is the level of acceptable performance based on variability of data in our reference data set, so our test set. So basically, not always, but most of the time, all our reference performance is going to be within this threshold, because this is what you as a user implicitly agreed to when you deployed a model after you evaluated that on your test set, because you said that the performance of test set is fine. So we take our threshold, which is based on number of standard deviations of the mean performance on your reference data set. Then we see this kind of strong lines that you see on the plot. So the lines that are not have no alpha value, so they're not transparent. And these are our point predictions for, let's say here, MSE. So if you hover over it, because it's interactive, you will see that MSE is, let's say, 9,449 point something, something, something. And this is a specific point prediction because we give you the point prediction. But of course, this point prediction is not going to be perfect. So what we do on top of that, we have so-called sampling error, which are basically just confidence bands around it. And this is your kind of uncertainty the algorithm says about its own prediction. So we not only estimate the loss of your model, but how certain are we that the loss is within certain limits. So we see here that it's MSE of 9.5 thousand plus minus 1,750. And then you will know that the MSE should be within these regions. It's quite likely to be within this region. And again, you see the same thing here. There is just one more thing, which is this kind of red diamond, which just shows you in a hopefully attention capturing way that there is something wrong going on. There is an alert because this value is above the threshold. So we said the drift has been detected and you know where that is. There is just one last thing, which is the chunk. And if you have your timestamps, we strongly encourage people to use timestamps with NannyML because then you can actually pick where, when the issue happened. In case in some use cases you don't have a timestamp because you just do different geographies, let's say, you'll be able to find what is the index of your data. So then when you do your own analysis, you can just select those index, and this is what it says in the chunk. So here we're dealing with analysis, dataset analysis partition, index 782 to index 1563. So if you select your data from the analysis point with these indices, you will get the data for which the estimated MSE is almost 2000, almost 20,000 here. Hope that explains the plot.
Yes, that was a very nice explanation. Thanks. Just a few more questions. So someone thanking you for the presentation, saying, hey, thank you for the presentation. And then what is the best way to estimate if the model is prone to data drift in the offline setup, sorry, before going into production? Is there a way to analyze it offline?
Yes, another question, and I think it's our roadmap to be a feature explicitly. If you don't want to do it with what we have here, what you should do is, first of all, attend the next webinar when we'll talk about data drift in more detail. But long story short, you should run drift detection algorithms on all your training and on your testing, and assume that your model is temporal. So don't shuffle your data, don't randomize it in some way. Do at most time series split, and then just analyze the drift there. If you see the drift already in your training and your validation in your test data, it's quite likely that it actually is prone to drift. That's one thing that you can do with NannyML. Another thing that you could do just fully manually is analyze, just split it into, again, in time series fashion, and analyze feature importance. If feature importance per split changes, then your model is probably drifting, and that might be an issue.
Nice, very nice. Do it in the next webinar though. But I will explain this in more details. There's another question that I will take. If we're gonna share the recording of the webinar, I already answered once, but yes, we will share the recording. And if you want it, please just drop us a message. We'll share it anyways, but please drop us a message on LinkedIn in our NannyML page and let us know that you're waiting for the recording, and we will send it to you ASAP. Otherwise, we'll send it next week. So this was it, and only 2 more questions, Wojtek. The first one, have you experimented NannyML with managing highly distributed environments, model failure like edge AI models?
You should click answer live. Oh, yes. So no, we haven't. When it comes to highly distributed environments, one thing we can say is that the algorithms themselves are reasonably well optimized. So they will run on edge devices, and they will run, roughly speaking, as fast as your actual model. Unless you use, quantized linear regression that is learning semi-fast, it's not going to be as fast. Generally, we are in the same speed performance region as gradient boosting models, because we lose a lot of gradient boosting underneath. When it comes to gathering the data and things like that, we're not ready for it, to be honest. So you would have to do a bit of engineering heavy lifting on your side. But then the core algorithms themselves can definitely be used on edge and with devices that are not that performant.
Awesome, thanks. One last question that is actually a follow-up question. Thanks for answering regarding the estimated performance plots. The follow-up, is it possible to define chunk sizes and also chunk content, so to say, manually while calculating estimated performance, or is it kind of already defined? Thanks.
So yeah, you can absolutely do it. And let me actually find it in our read the docs. How to do it. It's going to take a second, but long story short, there is a default way, but you can define it, and you can define it in a few different ways. So you can have, if you have timestamps, you can just define that you want it a chunk per week, and then it's going to automatically select data from a given week or from a day or from an hour. And another option is you can just define the size, so that's a size-based chunking, and you should be able to do it very easily. I mean, you will be able to do it very easily, so you can do it however you want. And let me just quickly share the screen here because I just found it. So you have these tutorials, and basically when you want to create chunking, you can have time-based chunking. When here you can just say what is your chunk period, and this is gonna just give you a quarter, so you'll be able to do it per quarter, per second, per minute, per hour, per day, per week, per month, per quarter, or per year. In size-based chunking, you just need to add an argument when you initiate the estimator, like we have here. We have CBPE, the exact same thing, and we just add another thing, which is chunk size, 3,500 or however many you want, and it's gonna give you an estimation. Of course, if you go with chunk sizes, let's say below 300, then the uncertainty bands will just explode, and it's not going to be very useful because of stochastic nature of data and machine learning. And you can also just, if you don't want to care about the data, the size of the chunks, but you want for some reason a specific number of chunks that you want to divide it for, maybe because you want to see how this kind of corresponds to, I know, cross validation and what's the stability in your cross validation, and you do 10 faults, then you can just put chunk number equal to 9 or to 10, and you'll get that amount of chunking. And if you don't do it, it's automated. I'm going to share that
yes,
here in the chat. And you can take a look.
Nice. Thanks a lot, Wojtek. Those were all the questions, lots of questions. So thanks a lot, everybody, for all your questions and all your attention during this presentation. And yeah, we hope to see you in the next webinar. Wojtek, if you want to say goodbye.
Yeah, thanks a lot, everyone, and hopefully see you next time.
Thanks a lot. Bye.